Hello everyone. Today we're going to present the topic, cryptography. Our membership includes 热神孔 and 朱元璋. Here is an encryption process. The encryption is used when we need to send a message secretly. So as distributed on the page, we have two user A and B. A and B share the common key, and A wants to send a message M to B. Instead of directly sending the message, A will encrypt the message with a key to generate a new string C, which means ciphertext. So after receiving the string C, B will try to decrypt the ciphertext C and get the original message using the key. If someone else wants to hack the system and got the message between them, he will only get the encrypted message and will need further steps trying to decrypt and get a real message. So generally, encryption methods are aiming to achieve the lowest probability for others to get a real message behind them, and in other words, achieve the highest security. So how do we ensure the security of the ciphertext? And generally, one-time pad refers to one of the cryptographic techniques that uses a random key to encrypt a message into ciphertext. The key is only used once and is as long as the message being encrypted. And here the one-time pad is secure because the ciphertext created after encryption for different messages are indistinguishability distributed, which means that if you cannot learn anything more about the original message by seeing the ciphertext. And for the encryption process, we have key and M, and we will do XOR operation for key and M and get a ciphertext C. And then if we want to decrypt the ciphertext, we will do XOR operation for C and key, and finally we can get the original M. So is the process secure? And yes, if key is used only once. So for the however, one-time pad is not that efficient as requiring a new key every time. So not considering many-time secure encryption. Many-time secure encryption refers to a cryptographic method that remains secure even if an attacker intercepts multiple ciphertexts encrypted with the same key. Our goal here is to generate a ciphertext that always in the same distribution, no matter what message is used. But unfortunately, such perfect, secure many-time encryption doesn't exist. But what we can do is to use some mathematical techniques to simulate this process. And computational randomness. Here intuitively, when it comes to randomness, we always mean security. So instead of using true randomness, we can simulate the randomness in a way called computational randomness. And assuming f is a function that generates the outputs in the computational randomness. Its outputs will be similar to a real random distribution. And the uniform distribution on the right side represents a real random distribution. The similarity is defined as computationally indistinguishable, which means we have a function p, and this function is bounded in polynomial time. And we cannot use the function p to distinguish the distribution on the two sides. But because we're simulating the true randomness on the right side, so if we cannot distinguish the distribution on the two sides, we can also think that the distribution on the left is also is also a random distribution. So how could that be achieved? Obviously, using NP functions. Note that at this time we're assuming P not equals to NP. Otherwise, such functions doesn't exist.
So how could we utilize the computational randomness? First, we introduce the one-way functions. A function is a one-way function if we can easily get the output from it, but it is hard to get input from the output by inversing the function. A one-way permutation is similar to the one-way function. Instead, it requires the input and output has the same length. Now, assuming we already have a one-way function, how would we generate a random bit? So here we introduce the hardcore predicate. Suppose we have a one-way function f. We said previously that the input x for a one-way function is hard to find. But what it actually means is that the entire x is hard to find, but maybe some bits could be found from the output. The hardcore predicate here would play as a role that transforms the partially recognizable x into a computational randomness. Here is a definition of a hardcore predicate function. It takes the same input as the function f and generates a one-bit output, which itself is a computationally randomness. Then it also allows the combination of the output from f with the predicate itself to form a computational randomness. In other words, the function g that generates the output as a combination of the one-way function f and its hardcore predicate p will generate outputs in a distribution that is computationally indistinguishable with the true randomness. With this method, we can generate a one-bit randomness from the hardcore predicate p and combine it with the one-way function to form a n+1 bit randomness. Also, there's a theorem that says every one-way function has a hardcore predicate, so such method should always work unless it is proved that p equals np. Finally, we introduce a little bit more in how to generate more bits of randomness. This could be done with the pseudo-random function. Such function takes a key and a string as its input and generate one-bit computational randomness. Here is its definition. If a one-bit randomness could be generated, then similarly, the random bits with longer lengths could be generated by using the function for several times and combining the results. By having multiple lengths of random bits, we can encrypt the message in a way similar to the one-time padding, which uses a computational random key each time instead of using the true random one. In this way, we will finally achieve a result closer to the previous goal of many times secure encryption, that the outputs are computationally indistinguishable no matter receiving word messages. That's all of our presentation. And here are some references. And are there any questions?